Okay, I've still got a couple of notes, stuff I scratched down at the end of lab last time. But we've seen this, okay? It's a parallel plate capacitor, totally impractical parallel plate capacitor. You would never use this in a circuit for anything, but it's a good demonstration. With the hand crank generator, we can generate up to maybe 50,000 volts, okay? This thing probably only hold maybe 10,000 because it's imperfect. It gaps. Okay, you get little sparks, and the spark discharges the capacitor. Okay, now as you know, though, what's happening is you hook this thing up, and that Wimshurst generator, that's what it's called, a Wimshurst generator, pulls electrons off of one plate and deposits them on the other. So you get the ones deposited on is positively charged, the one that negatively charged, the one that the electrons are pulled off is positively charged, and that ought to be completely obvious, okay? Because you have like electrons and protons being positively charged, you pull electrons off, that leaves protons that are no longer shielded by an equal number of electrons. So you have an excess of proton charge on one side, excess of electron charge on the other side. Now, what we want to do is just kind of analyze the capacitance of this thing and see what it might be. First thing we have to understand is that the electric field between these plates, okay, let's say plates are here, electric field between these plates is, if the plates are close together by symmetry, it has to be directed perpendicular to the plates, because the electric field of a given plate, again, by symmetry and by Gauss's law, is perpendicular to the plate, very close to perpendicular, as long as you're much closer to the plate than you are to the edge. Okay, so we know that the total electric flux of a charged plate, let's just draw this thing as a charged plate with, let's say, just a bunch of positive charge on it. Now, positive charge doesn't move around in metallic plates. The negative charge is what moves around. But you move a bunch of negative charges off, you got a bunch of positive charges. And then you have a side view, looks like this. You got equal number of positive charge, an equal number of positive charges on both sides. If you sketch what I'm sketching is like on this side, there's another disk. Side, another one. And then this whole thing is closed. So you surround this thing by something much like a wheel. That makes sense? Okay, now that's not the surface that we normally use for this thing, but I'm going to use that surface because it's a little easier to understand, and it makes the other one much easier to understand. You see what I mean? So this is the wheel surrounding that plate. What I'm saying is that if the wheel is thin, very close to the plate, almost all of the electric field escapes through the circular surface. Okay? So what you have is, you have an electric field like this. That far from the edges is very, very nearly perpendicular to the plate and therefore to the faces of this wheel-shaped surface surrounding the plate. Now down here near the edges, the field starts to do this. Now you got charge on the end here, and by symmetry, that last charge at the very bottom is going to have an electric field that's straight down, clearly does not escape through the circular surface. Does that make sense? Okay. So I say these escape clearly through the circular face of the imaginary Gaussian surface. You've seen that terminology, Gaussian surface, in the transition problem, have you not? Does that sound familiar? Well, if you haven't, that's a Gaussian surface. It's any surface you care to draw in order to figure out what the electric field of a configuration is, okay? And there's always got to be some sort of symmetry involved, or the Gaussian surface is worthless, okay? And the whole analysis can be worthless. Okay, so what I'm saying is, like, between here and here, we'll complicate this a little closer. These perpendicular lines escape through the circular face of the Gaussian surface. Okay, and the same on this side. Some of these down here, and there'll be some up here that escape, like this one, and this one are escaping through the non-circular part. It's like the surface of the wheel that meets the road. Now, I mean, this is a circular cylinder. We're talking about the sides of the circular cylinder, not the faces, the circular faces of the circular cylinder. Okay? And it's clear that some of these lines are going to escape, but most of them escape here. And if it's a really thin cylinder, then that boundary is going to be really thin. There's not going to be much area for the field to escape. Okay? So to the extent that this thing is close to the surface, the circular area is A. The flux is 4 pi k times the total charge contained on this one disk. Okay, this is just one of the disks. if all the flux is through the circular face of the Gaussian surface, then what's the electric field equal to? Um, what are you gonna use for the area? I think I said the area of the circular area is A, right? So is that the area of the Gaussian surface?
A is being the one in the middle, right?
No, that's not the Gaussian surface. Thing in the middle is the actual plate.
So the other two, I guess.
Yeah.
Gotcha.
Should be
Three,
2A, right?
2A, yeah.
I said the area of the circle is A.
Okay, yeah, then 2A.
Okay, now it's clear that, I mean, why is the electric field equal to the flux divided by the area? It's because the electric field is, the flux is the perpendicular component of the electric field times the area. Since the field is perpendicular almost everywhere, if it's a thin surface, okay? Then since the flux is field times area, the field is the flux divided by the area. That's something, of course, you just have to really deeply understand. And that's equal to there's your total flux, there's your total area. Okay? Make sense? Now, if you've got two plates, one of them positively charged, the other negatively charged. Well, I thought I had a picture of that. I must have gone up something else.
You did have one.
Yeah, we're recording, so. But the picture was this, and you'll be hopefully familiar with it. I used red and blue, but the blue was actually for the negative charge. So I'm not going to use red. I've already got the wrong color here. And we can see that the fields are opposite outside the plate, and they reinforce inside the plate, giving us a net field from this plate toward this plate. Now, this field has magnitude pi kq over A, and this blue field also has magnitude 2 pi kq over A, so that in the center, you have this net field 4 pi kq over A. It's between the plates of a parallel plate capacitor. Okay, well, that much is pretty simple. You should really understand that completely based on what you've been told in transition set 2 and whatever I've said that hasn't already been said in transition set 2. Okay, so my question now is, if the potential difference here is 10,000 volts, so and I understand, I say using 10,000 volts, you can use 10,000 volts if you like, but I'm just going to say I'll say given V and delta S, what is E? Now, what do I mean by V? Well, let's discuss it. Okay, so after some thought, people say, well, voltage and separation, you can get the potential gradient. Okay, so if it's 10,000 volts and the separation of 2 centimeters, which is ballpark what we have. You have 10,000 volts over 2 centimeters, which is going to be 5,000 volts per centimeter. That's your potential gradient. And that's your electric field. Now you want the electric field in volts per meter, which is equivalent to newtons per coulomb. And that's something that you should really be very familiar with from the transition problems so that you can think about more difficult problems, okay, more involved problems like this one, okay? So that comes out 500,000 newtons per meter, or 500,000 volts per meter, 500,000 newtons per coulomb, okay? If that's your electric field, and if 4 pi kq over A is your electric field, well, that means you're going to set 4 pi kq over A equal V over delta S. In this case, by centimeter squared, ballpark 300 square centimeters. So if you put it in the equation, you got this. Now, you don't want to have to think through the equation to understand that you're going to divide the number of volts by the separation. And it could be your electric field. That's something you just have to understand. That shouldn't come out of 6 pages of algebraic analysis of equations that you don't quite understand. Okay? That should be just an obvious thing that you understand that you could prove by equations and assumptions and principles and so forth. And you should know that the potential gradient then is the electric field. And I think you're about there, okay? I think that's something that's starting to make good sense to you, which is really pretty good progress, okay? So there's your electric field. And this is your electric field. K is just a universal constant. A is just the area of the plates. They have a 10 centimeter radius. You can easily calculate. They have roughly a 300 square centimeter area. And all this is approximate. We have no idea how close that potential difference is to 10,000 volts. But judging from the length of some of the sparks, we figure that's probably about the right order of magnitude. Okay, so we'll just assume that. Again, if you set that equally 4 pi k q over A, you're going to get Q. So take just no more than 2 or 3 minutes. You should know that K is approximately 9 times 10 to the 9th Newton meter squared per Coulomb squared. That's the only thing you don't know here. And I think somebody was talking about it and kind of knew that a couple of days ago. There's your K. We've got 10,000 volts and a capacitor with plate area. I'm just ballparking at 300 square centimeters, separation of 2 centimeters, right? Then very quick and easy calculation, which we actually did in lab last time, Friday, 3 days ago. We get about 500,000 newtons per coulomb or 500,000 volts per meter. Okay. And a volt being a joule per coulomb, if you divide by a meter, you divide a joule by a meter, you get a newton, so you have newtons per coulomb. And that should be totally familiar to you if you've properly prepared the introductory problem sets, because those are very those unit calculations are very fundamental and they're stressed. Okay, so you really do need to understand these units. Okay, so anyhow, there's your potential gradient. You can use either form. Okay. Now, it's equal to your electric field. That's what the potential gradient is. When you see it in newtons per coulomb, it's obviously the electric field, because you would multiply the electric field by your number of coulombs to get a force. If you multiply your field by your charge, you get force. Okay, your charge is in coulombs, and if you multiply E in coulombs, or a Q in coulombs, a charge in coulombs, by this, you're going to get a force in newtons, as you should. Okay, so there's your potential gradient. Looks like a 20 there, but that's a C for centimeters. Okay. Now, and I think I might have written something down here that wasn't right. Anyhow, since 4 pi k q equals your electric field, somehow something doesn't feel right about that, but let's work it out. So we have something's either not right about that or something not right about what I wrote over here. Yeah. Okay. It's actually 4 pi k sigma. It's the sigma in the intro sets. Okay, well, it's a charge per unit area, the charge density. So what I wrote down there just wasn't right. I omitted the sigma. We get this equals 5 times 10 to the 5th newtons per coulomb. 4 pi k is approximately equal. K is 9 times 10 to the negative 9th. Okay. Newton meter squared per coulomb squared. There. Well, if I multiply 4 by 9, I get 36. Multiply that by pi, I get about 110. So I'm going to say that's over about 1.1. This is just a ballpark. It'll be Newton meter squared per Coulomb squared because it's just a multiple of K. It's like 4 pi is like 12. Okay, closer to 12 and a half. 12 and a half times 9, well, 12 times 9 is 108. Half of 9 gets you up to about 110, which gets you 2 more orders of magnitude and a 1.1. Okay, so the numbers are very simple. So you get your sigma is, and I see where somebody got a 10 to the 6th time thing here. This is going to be approximately equal. I'm going to even ignore that 1.1 is different than 1. I'm going to say it's ballpark of 5 times 10 to the negative 6. If you do the units, you're not going to get coulombs. You're going to get coulombs per meter squared. Okay. Now you got to multiply that by the number of meters squared. Two is sigma times A, which is your this times 300 square centimeters. And that's coming out way too high. That's going to be way too many coulombs. Then you're going to get, ouch. That's 0.03 square meters. 0.03 times 5 is 0.15. So that'd be like 1.5 times 10 to the negative 7th coulombs. That'd be negative 8. No, I still think maybe it's negative 7th. 0.03 times 5 is 0.15. We move decimal over. And that's kind of what I get. Now, something's wrong with that, because I don't think it holds nearly that much charge. So somebody's got their hand up, so I did something ignorant. So somebody's going to correct me. I hope. Okay, somebody else got something with a 10 to the negative 9. That's a lot of charge, actually. If those plates had that much charge on it, I wouldn't want to be getting there. Okay. So something is wrong with some unit in this calculation, not the units, but the reasoning is pretty straightforward. Okay. So you go ahead and figure out if that's really right or not. It just, I don't want to belabor it. I'll think about it a little bit while you work on something else and figure out where in the world this fairly simple analysis went haywire. But the idea simply is from the voltage and the separation, you get the electric field. Okay. And the electric field is 4 pi K Q over A. Okay, or 4 pi K sigma now. Okay. And that's pretty intraconvertible. Intraconvertible. Going back to the etymology of that word I just used, and I don't think it works. But anyhow, it's intraconvertibly wrong. Okay. But reasoning appears to be intraconvertibly right. My numbers don't match my reasoning. And I mean, they're 10,000 square centimeters in a square meter. You had a 20 by 20 rectangle, you'd have 400 square centimeters. If you inscribe a circle inside, it's about 3/4 of that. should be 314.15926, whatever. Okay, 314.5926 square centimeters. So I don't know what's wrong here. Okay, but let's now ask, what if I move these? What if I move these plates to separation of 0.5 centimeters? What happens? Now, this means I charge the plates up to where they got 10,000 volts and they're holding maybe this much charge, okay? But I think that it's a couple of order magnitudes too high, at least. But they still have the charge. We don't allow charge to dissipate. We just move them closer together, right? So what happens? And I'll tell you, nothing visible is going to happen. Okay, we charge them up, we disconnect them from the generator, and they're sitting there, and we assume they don't leak any charge. But we move them twice as close together. What happens? What happens to what? Okay, well, I posed the question again. It's got 10,000 volts per centimeter. That's 2 centimeters apart. So what's going to happen if you move it to half a centimeter apart? And I see people punching their calculators, and I'm thinking, no. The way you look at this is it went from 2 centimeters to 0.5 centimeters. It's 4 times as close. Okay. You have 1/4 the distance, so you're going to have 4 times the potential gradient. Okay. And we did get that. Somebody punched a calculator to get that, which I thought was, a little unnecessary. Think the numbers are obvious. Then punch a calculator and make sure that the numbers are obvious as you thought they were, because I thought this is all going to be obvious, and I know I've got the wrong answer there. Okay. Still pretty obvious. I still don't know what I did. But anyhow, so you go back to what was the potential gradient? Here it is. Okay. It's going to become 4 times as great, which will be 20 times 10 to the 5th newtons per coulomb or volts per meter, which is 2 times 10 to the 6th. Okay. You have to do positive or negative work to move those plates closer together. And we're talking about positive or negative work against the electric field. We're not concerned about any friction or mechanical changes that might go on. Okay, one more thing now. Capacitance is Q over V, stored charge per volt. Okay. This Q is generally in units of charge, and V's in units of potential difference, which in SI units be a volt. Okay. What's the capacitance of this thing if we assume that this is actually the charge? We just divide this charge by 10,000 volts. One point 5 times 10 to the negative 11th coulombs per volt. Okay. A coulomb per volt has a name, it's called a farad. And these demonstration capacitors that we've been using are, I think they're all now 1.0 farad, which means that you can separate this incredible 1 coulomb charge, which is a heck of a lot of charge to store, just for a 1 volt potential difference. And a 1 volt potential difference comes from cranking that thing, that generator, about this fast. Okay? Yeah. And you can easily get 3, 4, 5, 6 volts. You can get up to double that, 10, 12 volts, but you tend to strip the gears so we don't crank them that fast. It means that this is on the order of 100 billion, or that's on the order of 100 billion times the capacitor of those 2 little plates. Now, when you make a capacitor, do you get more capacitance if the plates are close or if they're further? Okay, earlier, we said that if we move the plates 4 times as close, the electric field, the potential gradient is great. And my whole reasoning there was ridiculous. Okay. I said we maintain the 10,000 volts by removing the leads to the capacitor and holding things steady. And that was just absolutely wrong. That was really a bonehead thing for me to do. Okay, so let's correct that. The charge doesn't change. Okay, now I somehow said the 10,000 volts doesn't change, which was, got to get myself checked out here. Charge remain constant. What happens to the electric field? Well, electric field is where is it? It's 4 pi KQ over A, right? Okay. Because it's 4 pi, well, it just depends on the charge density on the surface. And what we said is it doesn't matter if this surface gets thin, no matter how thin it gets, that wheel surface that we have surrounding the disc, no matter how thin that thing gets, the 4 pi KQ isn't going to change. And the area isn't going to change. So 4 pi KQ over A is going to change. The electric field isn't going to change. So if we move plates to separation 0.5 centimeters, this doesn't change. What we did before, where we said it does change, is we kept charging it up. Okay, well, 4 pi K sigma doesn't change. So what does change? He doesn't change. Potential difference becomes 1/4 as great. Now, what happens to the capacitance? Capacitance, it's charge per volt, right? Is the charge change?
It's constant.
No change in your total charge, no change in your sigma, so your electric field doesn't change. So the potential difference being the product of the electric field and the separation becomes 1/4 as great. What happens to capacitance? Is it increase or decrease? You tell me, increase or decrease? It increases because you have the same charge for fewer voltages, for fewer volts. Okay? Really can't read that. Capacitor becomes 4 times as great. Capacitance becomes 4 times as great. So if you're trying to build a capacitor, what you want to do is you want to take, oh, say a square mile of very thin sheet. Okay? And then you put some kind of a very thin insulator over that sheet. And then you roll it up. And you got a mile-long capacitor. It's maybe this big around. Whole mile of stuff rolled into here. Not only that, but that sheet that you put between it is a dielectric that enhances the electric field. If you enhance the electric field without changing the charge, that means you get even more charge per unit of volt. Okay, when I say enhance the electric field, you actually reduce the electric field between the plates. Okay, getting things, saying things backwards today. So there we have it. Now, okay, my point is these things that I want to be talking about, especially after break, go back and depend heavily on your close familiarity with these transition problems that we spent half a semester on. Okay. So you really need to continue working on nailing those. And of course, the ones on magnetism are new this week. We're going to talk about some stuff with magnetism next time. In lab last time, we demonstrated that changing flux is what creates an electric field. Okay. Current creates a magnetic field. Okay. And those are just 2 of the 4 basic things that underlie all of electromagnetism. Another one is Coulombs law, which is something we already know about. Okay. And these lead to Maxwell's equations, which are expressed in the language of multivariable calculus. And their solutions involve some really hairy partial differential equations that we're not going to be talking about. But we will talk about the Maxwell's equations mean, what they do in terms of things like gradients and cross products and so forth. Okay?